So we've gone from resonance, where we said kind of avoid carbocations at all costs if you can, right? To the last video that we talked about was we're making carbocations on purpose and then using them to do these reactions and all that other kind of stuff. And so I think it's worthwhile to kind of take a minute, talk about carbocations, and think about what makes them, which carbocations should we be making, which ones can't we make, and so on and so forth, and what helps make a carbocation stable, if we can even say that a carbocation is stable. And so when we did our addition reaction, so I'm going to go back to just using HCl because that's a nice reactive acid. Let's say that we have an alkene, a pi bond that looks like this, and we're adding HCl to it. And we know that the first thing that's going to happen is that pi bond is going to come get the hydrogen. And it's going to make a sigma bond to the hydrogen. It's going to break a sigma bond between the hydrogen and the chlorine, and we're going to make a carbocation. And when we used 2-butene in previous examples, it said it didn't really matter where we put the hydrogen. So we could put the hydrogen at this position and make the carbocation out here, or we could put the hydrogen at this position and put the carbocation on the ring. And so this is something that people kind of wanted to know. When we run this reaction, do we get a mixture of these two carbocations? Because of course, you're also getting your conjugate base, Cl minus. And so depending on which carbocation you generate, that Cl minus might be adding to this carbon, if that's the carbocation, or it might be adding to this carbon out here, if that's the carbocation. And so a bunch of people ran these experiments, and what they found is that the only product that you get out of this reaction is with the chlorine at this position here. This is the only product. Right? And so this carbocation is the only carbocation that gets made. So this has some shorthand now. This is called Markovnikov's rule. Markovnikov was, of course, a Russian scientist. And Markovnikov's rule says that the hydrogen will be added to the less substituted carbon of the alkene. Okay, so what does that mean? When we look at our alkene, I'm going to use the same one that I used up there. I'm just going to redraw it, right? When we look at our alkene, we look at how many carbons is each carbon connected to, right? And so we're only considering these two carbons that are part of the alkene, right? So this carbon here is only attached to one other carbon. Attached to one other carbon. And so we call this a primary carbon. You may remember a little of this from nomenclature, right? This is the same idea. This carbon over here is attached to three other carbons, one there, and then one over here. And so this is a tertiary carbon. So I don't know, we'll draw an arrow through here. Attached to three carbons. So it's tertiary. And so when we talk about this more substituted or less substituted carbon, what we mean is how many other carbons is that atom attached to. And so in this case, the one that's attached to one other carbon is less substituted than the carbon that's attached to three carbons. This is obviously more substituted. Now, a couple of important things. One, you only compare the carbons that are part of the double bond, right? This carbon is primary, this carbon is tertiary. This one over here is secondary, but it doesn't matter because that's not part of the double bond, right? Because the double bond is the base that kind of kicks this whole reaction off. And so we're only concerned with, does the carbocation go to the primary position in our first structure here, or does it go to the tertiary position like this structure here. And of course, we find out that the hydrogen goes to the primary position, the carbocation ends up on the tertiary position, and that means that your heteroatom will always add to the more substituted carbon. Right? So in the case where we had 2-butene in the previous video when we talked about substitution, it didn't matter because both of these positions are secondary, right? This carbon is attached to 2 other carbons. This is a secondary carbon. This carbon here is attached to 2 other carbons. This is also a secondary carbon. And so in this case, there's no Markovnikov's rule doesn't tell us anything because there is no more substituted or less substituted carbon for this alkene. Everything has the same substitution. And so if we put the hydrogen on carbon 2 or carbon 3, it does not matter. Right? It doesn't make any difference because you still make the same kind of carbocation. So Markovnikov's rule says the hydrogen will always add to the less substituted carbon, and the heteroatom, in this case chlorine, will add to the more substituted carbon. So that's a nice, sorry, I'm going to come back and talk to you guys. That's a nice rule. It tells us what to do, but it doesn't really tell us why, right? And the answer of this is actually very close to all the ideas that we've already been discussing, right? The answer to this is because we always make the most stable conjugate that we can. And so which carbocation, which is the conjugate acid of our alkene, which conjugate acid do we make? We always make the more stable one. So I wasn't done with this one yet. Let me go back. So in this case, right, which of these two is the more stable conjugate acid? It turns out that the one with the carbocation at the tertiary carbon is the more stable conjugate acid. Okay. So a rule. This isn't Markovnikov's rule, but we try to make the most stable cation possible. Okay, and so that means that if we have a choice, so whatever, I don't know, we can do whatever we want, but if we have a double bond like this double bond has a primary carbon here and a secondary carbon here, right? Only attached to one carbon on the end here, only attached to, or this one is attached to 2 carbons, right? Where do we put the carbocation? We put the carbocation on the more substituted carbon. So if we're doing this with sulfuric acid and H2O, right, we're going to use H plus and H2O. Our double bond goes and gets that H plus, and what we get out is we're going to get the hydrogen attached to the less substituted carbon and the carbocation on the secondary position, which makes it more stable. The reason that more substituted carbons are more stable, more substituted carbons are more stable for carbocations The reasoning behind this is that the more sigma bonds equal more electrons, whoops, and those electrons can kind of, right, having negative charge near that carbocation, they stabilize it to a certain extent, right? So the negative charge is surrounding that positive charge. The more negative charge you have, the more sigma bonds you have, the more electrons you have around. The more electrons you have around, the more they can kind of be negative to counteract that carbocation's positive nature, right? So at a primary position, there aren't that many sigma bonds around, right? There's at this primary position, there's only 2 hydrogens and 1 carbon-carbon sigma bonds. And so that position is not terribly stable for a carbocation because it doesn't have any electrons to kind of balance out that positive charge. A secondary position, you have a hydrogen, but you also have 2 carbon-carbon bonds, and those carbons have other bonds to them. And so you have more electrons surrounding that secondary position, and that makes the secondary carbocation more stable. So Markovnikov's rule applies to all of the additions that we've talked about, right? So Markovnikov's rule applies to addition reactions of HBr, HCl, HF, HI, and any kind of H plus H2O reaction, right? So remember, anytime we see sulfuric acid or anything like that, we cross out sulfuric acid and write H plus, and that'll do it, right? So any of these reactions will create a carbocation, and that carbocation will always be created at the more substituted position, and then our conjugate base comes in and reacts with that carbocation in the way that we talked about in the previous video. So carbocation stability is all based on substitution, right? The other thing, one more thing that I wanted to talk about was the other thing that stabilizes carbocations is, of course, resonance. So don't forget about resonance. So, oh, come on. So stabilizing carbocations boils down to two things. One is substitution, right? More sigma bonds equals better. And so a tertiary carbon, whoops, I'm in the wrong place. Sorry about that. A tertiary carbon is going to be more stable than a secondary carbocation, is going to be much more stable than a primary carbocation, right? Primary carbocations don't really exist, right? So we're almost always going to be making secondary or tertiary carbocations instead. The second thing that stabilizes carbocations is resonance, right? So we're still not out of the woods on resonance yet. So if you can make a carbocation that has a resonance structure, right? A pi bond near carbocation, that pi bond can move over. We can make pi bond to pi bond move. And that resonance structure is then going to be that, right? If we can distribute that positive charge, that's going to make it more stable. So watch out for those pi bonds near carbocations, because that resonance can also stabilize a carbocation. So if you have a secondary carbocation that has resonance versus a secondary carbocation that doesn't, you will always form the secondary carbocation that has resonance, right? So keep that in mind as you make your carbocations, and as long as you make the carbocation in the right place, the rest of it follows pretty well from there. So there's a worksheet. The worksheet has a couple of rearrangements on it. So we're not going to talk about rearrangement this week. I think we'll get into rearrangement at the very beginning of next week, because carbocations move around to make themselves more stable, which is interesting and fun and makes everything just that much more complicated. But carbocations can rearrange. We'll talk about that next week, and then we'll get into all the rest of the addition reactions and just kind of blitz through all of our addition reactions. We've got a bunch more to do before we get to the end. So more addition reactions, more reactions of alkenes. They'll be very similar in some ways, and then we'll talk about carbocation rearrangements next week. So stick around for that. See you soon.